In this lesson, we will examine some properties of consecutive integers. Now, consecutive integers can be thought of as any successive string of values from the list shown here. So, some examples of consecutive integers include 1, 2, and 3, -7, -6, -5, and -4, as well as 3 and 4. Okay, now let's make some observations. We'll begin by examining integers that are divisible by 2. The important observation here is that every second number is divisible by 2. Next, if we examine all of the integers that are divisible by 3, we will see that every third number is divisible by 3. Similarly, every fourth number is divisible by 4, and every fifth number is divisible by 5. In general, every nth number is divisible by n. Okay, so how does this help us? Well, if we have two consecutive numbers, any two consecutive numbers, we know that one of those two numbers must be divisible by 2. In other words, one of the two numbers must be even. Similarly, if we have any three consecutive numbers, we can be certain that one of those three numbers must be divisible by 3. We can also be certain that at least one of those numbers will be even. Now, from these observations, we can formulate a rule that says if we have n consecutive integers, then one of those numbers must be divisible by n. Okay, now that we've learned a few things about consecutive integers, we need to be able to spot them. For example, we already know that these are consecutive integers, but we also need to be able to recognize that these will be consecutive integers just as long as n is an integer. For example, if n equals 7, then n plus 1 will equal 8, in which case we have two consecutive integers. Similarly, if n equals -4, then n plus 1 will be -3, in which case we still have two consecutive integers. Similarly, if n is an integer, then these will be consecutive integers, as will these and these. Okay, now let's apply this information. If n is an integer, what conclusions can we make about this expression? Well, if we recognize that we have two consecutive numbers here, then we can be certain that one of those two numbers must be even. And if we know that one of the two numbers is even, then we can also be certain that the product of the two numbers will be even. Okay, what about this expression? What conclusions can we make here? Well, to begin, let's take this expression and factor out an n. From here, we can take the n squared minus 1 and factor it to get n plus 1 times n minus 1. Finally, if we rearrange these terms, we can see that we have three consecutive numbers here, which means at least one of those three numbers is even. Now, if at least one number in the product is even, we know that the prime factorization of the expression must have at least one 2. Okay, what else can we conclude? Well, if we have three consecutive integers, we can also be certain that one of those three numbers will be divisible by 3. Now, if one of the three numbers is divisible by 3, then there must be a 3 in the prime factorization of the expression. Finally, since the prime factorization has a 2 and a 3, we know that the expression must be divisible by 6. So, these are some examples of the conclusions we can make if we are given a question involving consecutive numbers. Now, to finish this lesson, let's revisit a practice question that we examined earlier. When we first tackled this question, we used a table to study all of the possible cases. Here we noticed that the expression was even in all 4 cases, so we correctly chose B as our answer. Now let's try a different approach. We want to determine how the values of P and Q affect whether this expression evaluates to be odd or even. Now, if we recognize that these two numbers are consecutive integers, then we can be certain that one of those numbers is even. Subsequently, if we know that one of those numbers is even, we can be certain that the product must be even. If the product must be even, then the correct answer is still B. So, given the many conclusions we can make about consecutive integers, be sure to watch out for them. Just remember that they are sometimes found hiding in very unlikely places. In this lesson, we'll examine remainders. Now, up to this point in the module, we have focused primarily on numbers that are divisible by other numbers. For example, we've learned that 21 is divisible by 7. We know this because when we divide 21 by 7, we get an integer, and that integer is 3. Another way to express divisibility is to say that 21 is divisible by 7 because when we divide 21 by 7, we get 3 with no remainder. In other words, the remainder here is 0. Conversely, if a number is not divisible by another number, we'll get a remainder other than 0. For example, 11 is not divisible by 4. And notice that when we divide 11 by 4, we get 2 with remainder 3. In other words, 4 divides into 11 2 times with remainder 3. Now, there are various ways to denote remainders. In school, you may have expressed remainders this way, where the part after the r denotes the remainder. Here's another way to express remainders. Here, the part inside the parentheses is the remainder. Now, this is the notation I'll be using in this module, but you may see different notation in other resources. Also note that this remainder notation applies only to questions involving remainders. So, for example, if you see this notation in any other context, it will stand for 2 times 3. Okay, just to be sure that you fully understand this concept, let's look at a few more examples. When we divide 67 by 10, we get 6 with remainder 7. When we divide 21 by 5, we get 4 with remainder 1. And finally, when we divide 45 by 9, we get 5 with remainder 0. This, by the way, means that 45 is divisible by 9. Now, I should mention here that the concept of remainder only applies to positive integers. So you will never encounter a remainder question that has negative values. Okay, now let's examine some terminology. Here we have 11 divided by 4 equals 2 with remainder 3. The 11 here is called the dividend, 4 is called the divisor, 2 is the quotient, and 3 is the remainder. Now, an important feature about remainders is that they are always greater than or equal to 0 and less than the divisor. For example, if we take some number, n, and divide it by 7, the remainder will be greater than or equal to 0 and less than 7. Now, to solve questions involving remainders, we'll need some specific skills. The first skill is listing possible values. So let's say we're given some information about x. We're told that when x is divided by 7, the remainder is 2. So what are some possible values of x? Well, we're looking for numbers such that when we divide them by 7, the remainder is 2. So one possible value is 9. 9 divided by 7 equals 1 with remainder 2. Perfect. Another possible number is 16. What are some other ones? For example, is there a number less than 9 that has remainder 2 when we divide it by 7? Yes, 2 satisfies this condition, because when we divide 2 by 7, we get 0 with remainder 2. Now here comes a very important observation. Notice that 9 can be expressed as 2, the remainder, plus 7, the divisor. Similarly, 16 can be expressed as 2 plus 7 plus 7. So, to find other possible values of x, we'll keep adding 7 to the previous value, and so on. Now, in general, if we're told that some number n divided by d yields a remainder of r, then the possible values of n will begin with the remainder r. The next possible value will be r plus the divisor d, then r plus 2d, then r plus 3d, and so on. So we now have a formula for listing possible values of a number if we're given information about the remainders and the divisors. Let's test out this rule with an example. When w is divided by 8, the remainder is 3. So what are some possible values of w? Well, the remainder here is 3. So this will be the first possible value of w. Next, since we're dividing by 8, this is the divisor. So to find other possible values of w, we'll add multiples of 8 to the remainder of 3. So the next possible value of w is 3 plus 1 8. Then 3 plus 2 8s, then 3 plus 3 8s, then 3 plus 4 8s, and so on. When we evaluate these, we get the following as possible values of w. Alright, the next important technique is to rebuild the dividend. Here's what I mean. If we take the dividend 11 and divide it by 4, we get a quotient of 2 with remainder 3. Now we can take these three values and use them to create an equation that ends up equaling the dividend of 11. We can write 2 times 4 plus 3 equals 11. Similarly, since 34 divided by 5 equals 6 with remainder 4, we can take the three values shown here and use them to create an equation that ends up equaling the dividend 34. We can write 6 times 5 plus 4 is equal to 34. Let's try one more. Since 8 divided by 11 equals 0 with remainder 8, it must also be true that 0 times 11 plus 8 is equal to 8. In general, if n divided by d equals q with remainder r, then it must also be true that q times d plus r is equal to n. Let's now take this rule and use it to answer a question you might see on test day. You might want to pause the video now and try the question before continuing. Okay, the question tells us that when 5 is divided by b, the quotient is 2 and the remainder is c. From here we can apply this rule to conclude that 2 times b plus c must equal 5, which means the answer here is b. Okay, let's summarize. In this lesson, we learned some important skills for tackling remainder questions. In this lesson, we'll review some of the important problem-solving strategies we examined in this module. We'll do this by individual topic. For example, for questions involving divisors, factors, divisibility, and multiples, one strategy is to reword the question or information to see if this will help gain some insight into the solution. Don't forget that for integer property questions, there are several different ways to say the same thing. Another important strategy is to consider finding the prime factorization of key numbers. In particular, when you encounter a number greater than 100, you should consider rewriting the number as a product of prime numbers, since the solution may depend on this. Now, when it comes to questions involving prime numbers, it is important that you have memorized the prime numbers up to 59 at least. On test day, you do not want to be determining whether or not 51 is a prime number. Also, when it comes to questions with prime numbers, keep in mind that every prime number is odd with just one exception. 2 is the only prime number that is even, and there are many questions that test this fact. Next, for questions involving squares of integers, also known as perfect squares, you will find that the majority of questions are testing your knowledge of one of these two rules concerning perfect squares. When it comes to questions involving greatest common divisors, or least common multiples, the most important point to remember here is that you probably have some options. One approach is to apply the prime factorization technique and then use some logic to solve the question. Another common approach is to choose some numbers that meet the conditions defined in the question, and then see what conclusions can be drawn. Now, this isn't to say that these are the only approaches, or that either of these approaches will always work. The important point here is that there are often two or more ways to solve a question, so you should take some time up front to identify possible approaches, and then apply the one you feel will be the fastest. Now, for questions that involve the greatest common divisor and the least common multiple, you should consider applying the formula that ties these two concepts together. Next, for questions that involve even and odd numbers, you must know the following rules. Also, these two extensions are tested frequently, so keep them in mind. Finally, if you encounter a question where you must determine whether an expression is even or odd, you should consider testing each possible case. When doing so, you have two options. You can use E's and O's to represent even and odd numbers, and then apply rules to evaluate each case. Or you can plug in actual even and odd numbers. Now, for questions involving consecutive integers, you must know how to identify consecutive integers, since they are often disguised using variables. Also keep the following rules in mind when tackling questions with consecutive numbers. And finally, when tackling questions involving remainders, remember that you can often solve these questions using more than one approach. The two primary solution techniques are rebuilding the dividend and listing possible values of the dividend. Finally, don't forget that some remainder questions have implications that involve divisibility. For example, if a number is divisible by x, then the remainder will be 0 when that number is divided by x. Conversely, if a number is not divisible by x, then the remainder will be a number other than 0. Okay, that concludes the summary of strategies for integer property questions. Now it's time to apply them by tackling dozens of questions.